you have learned that in our natural coordinate system, we can write the shape function in terms of 1 minus xi by 2 and 1 plus xi by 2. Okay. Now here, this is the correlation between the xi and x. Basically, this is the correlation between our natural coordinate system and our physical coordinate system. So here we can write xi like this. So here we can see, so when xi change between +1 to -1, x is changing from x2 to x1. So here 1 minus in bracket -1, and at denominator we have x2 minus x1. Okay. Now here we are getting change per unit length, change per unit x, and this one basically x minus x1 at any point here. Okay, that should be x minus x1. And if you want to represent in terms of xi, then we should minus this value -1. Okay, so this is the correlation between our natural coordinate system and our physical coordinate system. Okay, now we can simplify this one like this: xi is equal to 2 in the denominator x2 minus x1, and this part here x minus x1 minus 1. And this can be further simplified like this. Here x2 minus x1 is nothing but your L. Okay, so if this is our xi, you'll observe that when we write the shape function in our natural coordinate system and try to derive the stiffness matrix in our physical coordinate system, when we try to derive the stiffness matrix, that time we need to have our correlation between the xi and the x. Okay, xi and the x, and there you will observe we are basically doing dx by dxi, which is to be our Jacobian J. So you will observe there is a role of the Jacobian in deriving the stiffness matrix from our natural coordinate system to have our real valued stiffness matrix. Okay. Now here this is our correlation. Okay. Now if you know that our shape function is our 1 minus xi by 2 and 1 plus xi by 2, then in that case displacement at any point can be written as a summation of n1 u1 plus n2 u2. Okay, and that also can be written in this form also. Okay, in a matrix form we can write like this. Okay, and here you also observe that value of the shape function n1 will be 1 at -1, and this will be 0 at second node. Similarly, value of n2 will be 1 here and will be 0 here. So this is the property of the shape function, and the shape function is varying linearly within the element, and the stiffness matrix is derived using this shape function, which is called the linear element. Okay, if you use higher order element, in that case you can say that it's quadratic element, because our shape function will be in the nature of quadratic. Okay, so here this is the shape function for this 1D bar element. Now we know that the strain that is equal to du by dx. Strain is our du by dx. But problem is that u we have written in our natural coordinate system. Okay, so we need to convert it. Okay, so what we can do, we can use the chain rule system like this. Du by dx we can write like this: du by dxi and dxi by dx. Okay, and for the same reason we basically try to derive the relation between the x and the xi. Okay, so the strain is your du by dx. Using chain rule we can write like this, there is nothing wrong. Okay, so again we know that u is equal to n1 u1 plus n2 u2. u1 and u2 nothing but the nodal value, that are the constant value. Okay, that are the constant. n1 we already know, n1 is equal to 1 minus xi by 2, and n2 here 1 plus xi by 2. So what we can do, we can take the derivative of u with respect to xi, and we can write like this. So d xi in bracket 1 minus I by 2 u1 plus 1 plus I by 2 u2. Okay, and that will be your minus u1 by 2 plus u2 by 2. So we can simplify like this, u2 minus u1 by 2. So here du by d xi is u2 minus u1 by 2. Okay, so here this value is going to be u2 minus u1 by 2. Okay, now already we have derived the relationship between the xi and the x. So what we can do, we can take the derivative of xi with respect to x. Okay, so d xi dx is nothing but 2 times x2 minus x1. Now note that Jacobian is nothing but your dx by dxi. Okay, so Jacobian will be your x2 minus x1 by 2. So here, if you write dxi here, then this is the Jacobian. Okay, so here from the relationship between the xi and the x, we can obtain dj by dx, which is required for our chain rule, and dx by dxi is the Jacobian for 1d per element. Okay. Okay. Now what we can do, we can basically try to get the strain, which is nothing but du by dxi times dxi dx. So from here we can write the strain like this. So now here strain is your u2 minus u1 by x2 minus x1. So here you can write that strain is nothing but u2 minus u1 by L, which is already known to us. Already in our first year or second year courses, already you have learned that strain is nothing but delta U by L. So that part we have basically derived from our natural coordinate system also. Okay. Now here we got the strain. The strain quantity we are writing in this form. The strain already we have learned this one u2 minus u1 by L. So that part basically we are writing in this form, in the matrix form. You just try to see u1 minus 1 plus u2 by the L. Okay. So this equation we are writing in a matrix form like this. And we can say this part is nothing but the B. So we can write B transpose, we can write B transpose E B integration of the volume, that is the K. So already we know that K is nothing but B transpose E B dB. Okay, that is the integration of the volume. This is true for the 1D per element. Okay, now further simplifying this, what we can do, we can change this integration over the length 0 to L B transpose E B, we can write dV, and here we can write area A. Okay, so now, so it should be dx, it should be dx, it should be dx. Okay, this should be dx. Okay, now we can write integration 0 to L B transpose E A times B dx. This part we can say D. Okay, so stiffness matrix, so the stiffness matrix K we can write in this form. Okay, now B already we know B is nothing but minus 1 by L and 1 by L, and this one, and we know that K is nothing but B transpose dB, that is integration of the volume. So here what we can do, we can put the value of B here and we can write like this. Okay, so here you just see we have B, we can write like this, minus 1 by L and 1 by L. So here we are writing minus 1 1 by L, we are basically 1 L we are keeping outside. Again we have B, so minus 1 1, so there's 2 L, so here we have L square. E and A is the constant term we are keeping out of the integration. Now we have this one only. We have stiffness matrix K is nothing but EA by L square, and E of L square and integration -1 to 1 times -1 to 1 dl, or you can write dx also. So now if you multiply and do this integration, you'll observe we are getting 1 L here. So this L square will get cancelled out, then we will get the stiffness matrix like this, EA by L and 1 minus 1 minus 1 1. This is the stiffness matrix for the truss element. Okay. Now this integration we have done in our physical coordinate system. Okay. Now, if you want to derive this stiffness matrix in our natural coordinate system, in that case, our limit will change from -1 to 1. So here, if you want to do the integration, over the -1 to 1, if you want to do the integration in our natural coordinate system, in that case, our integration will look like this. So here, basically, you just see we are driving the same thing here. Already know the relationship. From there, we are basically getting dxi. Okay, basically what we are doing, we are basically doing the dxi by dx. From there we are getting this value. Okay, and we know Jacobian is nothing but dx by dxi. So dx by dxi is nothing but x2 minus x1 by 2. Okay, dx by dxi is nothing but x2 minus x1 by 2, or nothing but your L by, or you can say L by 2. Okay, so dx by dxi, which is the Jacobian, okay, it is L by 2 for this case. Now here, you should always remember the Jacobian should be positive. Always Jacobian should be positive. For 1D per element, we are getting Jacobian as a constant value, which is nothing but L by 2. But if you have two-dimensional element, in that case, Jacobian also will be matrix. In that time, what we need to do, we need to consider the determinant of the Jacobian, and which should be positive values. Okay, so here we have tried to derive the relationship between the xi and the x. That is the relationship. Okay, so now what we are going to do, we are going to write this equation in our natural coordinate system with the limit of -1 to 1 b transpose EAB. Instead of dx, we are getting the Jacobian times dxi. Okay. Now here, if you do the integration, what will the value of it? It should be like this. K is your B transpose EAB, B here L by 2 and 2. So here 2 will get cancelled out. So here we will have B transpose E A B here L. So if we do this integration, you will observe that stiffness matrix is coming out to be E A by L here 1 minus 1 minus 1 1 like this. Okay. Now if you do the direct integration, analytical integration, we can achieve this one. Okay. Now here our aim is to convert these things into Gauss integration method or Gauss Quadrature integration method. Okay. So here this regular integration we need to convert into our numerical integration. Okay. So next, what we are going to do, we are going to use the Gauss Quadrature integration for this. Okay, so now here what we will observe that K matrix is nothing or B transpose EB x2 minus x1 by 2. It is also AL, and here we have this integration value -1 to 1. Okay, now if you use two Gauss point, okay, if you use two Gauss point, in that case our weight value is basically 1 and 1. Both are 1 and 1, and we are basically measuring at the value of -1 by root 3, and we are measuring +1 by root 3. Okay, since this value is a constant value, it is the 1. So your function f of xi is nothing but 1. Okay, so f of xi1 will be 1, f of xi2 will be 1. So here we will have the value of 2. So here we have B transpose EAB, and then we have here L by 2, and to here 2 will get cancelled out. So we will have B transpose EAB times L. So now here if we do this multiplication, we can achieve this matrix. So this is the basically stiffness matrix of 1D bar element. And if you want to calculate the stress and the strain. In that case, what you need to do, you need to first find the displacement at nodes u1 and u2. In that case, what you need to do, you need to write f is equal to k times u, or k times u is equal to f. And once you apply the boundary condition, and if once and you solve it, you can find u1 and the u2. Once you are able to find u1 and u2, then we can find the strain. Strain is nothing but v times your u1 u2. Okay, v times the u you can write, and once you find the strain, you can find the stress like this. Stress is nothing but E times epsilon. Okay, so here you can see what we did. We basically write the strain nothing but b times u, that is nothing but b1 b2 times u1 u2. Okay, so already we know the b is nothing but your B is nothing but your minus 1 by L and 1 by L times like this. Okay, so we can obtain the strain. Once we find the strain, if we multiply with the E value, we also can find the stress there. So this is basically we need to solve our trust problem. So here what we have learned that the shape function of 1D bar element in our natural coordinate system is your 1 minus I by 2 and 1 plus I by 2. From there, what we did, we try to correlate the relation between the xi and the x, and from there we basically obtain d xi, and we also obtain dx by d xi, which is nothing but the Jacobian. Okay, and then basically we obtain the relationship for the strain, and we obtain the B matrix. Okay, in this case B is to be your vector, but if we have 2D problem, in that case B will be a matrix. Once we obtain the B, we can get the stiffness matrix like B transpose dB, which we did for the volume, or the integration over the volume, and here D is nothing but the Young modulus, and at the end we obtain that stiffness matrix is your EA by L minus 1 1 minus 1 1 like this. Okay, once we obtain the stiffness matrix K, we can solve it and we can obtain the nodal dispersion value E1 and E2. Once we obtain this nodal dispersion value, we can calculate the strain. We can calculate the strain like this. Okay, and once we obtain the strain, we can get the stress quantities. Next, we are going to solve a 1D bar problem. Okay, thank you.